Hello, students. We need to talk about organic nomenclature. And in this section, we're just going to do alkanes. We're not going to do alkenes, alkynes, alcohols, amines, ethers, anything like that. Just our basic alkanes. Now, who came up with how to name molecules? Well, the International Union of Pure and Applied Chemistry, which is called IUPAC, has given us rules so we can be consistent and know what one lab says that they use will be the exact same thing in another lab that has that label on a bottle. All right, so then we can replicate experiments and do chemistry safely. So the current system is called substitutive nomenclature, which is right here. And what does that mean? Well, it means that we're going to take a basic alkane like ethane here, and we're going to rip off a hydrogen, all right? So it goes bye-bye, and we're going to substitute something else in its place. Now, I could have ripped off any of those hydrogens. I just chose that one. So now we have substituted a chlorine in place of that hydrogen right there. So that's where we get the substitutive nomenclature name. Now, rules for naming alkanes. These can be extended to other substances, the things that I mentioned before, like alkenes, alkynes, alcohols, ethers, amines, on and on and on. And as we do other chapters, we will do the nomenclature for those specific kinds of molecules. So let's get to the rules. Now, number 1 says, unbranched alkanes are named according to number of carbons. Now, what a branch is, we'll get to that in just a second. The important part of this rule is that our alkanes are named according to number of carbons. So if you have 6 carbons, as in this molecule right here, you're going to be a hexane. And if we scroll back through our lecture slides, we can see on this slide right here, if you've got 1 carbon, you're going to be methane, 2 carbons, ethane, 3 propane, 4 butane, 5 pentane, 6 hexane, and on and on and on. So each one of those is going to have its own name. And again, it's going to depend on the number of carbons. So let's go back to our slide that we were working on. Okie dokie smokies. So let's look at the 2 molecules below and let's decide which chain is the longest continuous carbon chain, because we're going to identify this as something called the principal chain, also called the parent chain. And we're going to start there when we name things. So if we look at the molecule on the left, we can see that we've got 1, 2, 3, 4, 5, 6 carbons straight across. So again, that's the longest continuous chain. So what that is a carbon chain where you don't have to pick up your pencil and go to another one. So we would not call this carbon number 7 down here and say that because this molecule has 7 carbons, it must be a heptane. No, that's not how it works. So on the molecule below, we can number it forwards or backwards, and we'll get to numbering in a little bit. But what we can see here is that this molecule is going to be some form of hexane. Now you can see that this molecule right here is different from this molecule right here because the bottom molecule has something dangling off of that, and we call that a branch. So a branch is going to be anything that's hanging off our principal or our parent chain, and it will be something that replaces a hydrogen of the original parent chain. So what you'll notice right here is that carbon only has one hydrogen. It doesn't have two hydrogens like the carbons around it, or three hydrogens like the end carbon. I also want to point out this weird thing on the left side. See how this says H3C? That's the exact same thing as CH3. Chemists just like to write it backwards like that to emphasize that the H's are on the outside of the molecule on that side. It's just one of those weird, quirky things that chemists do to confuse students. I'm sorry about that, but it's the exact same thing. All right, so this has 6 carbons in its longest continuous chain. Now, if we tried to do another chain, what we would see is we could have this one right here as a continuous chain, again, meaning that we don't pick up our pencil and go to another carbon, but that would only be 5 carbons long. And 6 carbons is obviously bigger than 5 carbons, so we're going to go with 6. We could also do this direction right here, but that would give us 1, 2, 3, 4, and that's even shorter than the 5 carbon chain. So the longest continuous chain is hexane, which is 6 carbons. Now let's look at the molecule on the right. So we might be tempted to go left to right because that's the easiest thing to do, and that's what most students want to do. So we could go 1, 2, 3, 4 and say that the parent chain is a butane. But do you see how we can make a continuous carbon chain without picking up our pencil, carbons bonded to each other, that's longer than 4 carbons? Well, hopefully you can see it. And how that would work is that we would number 1, 2, 3, 4, 5, 6. So that would be a hexane. Again, 6 carbons in your longest continuous chain. It's going to be some form of hexane. Now this would be the longest continuous chain right here. And we would have that CH3 hanging off, and that would be our branch. Now how we say where the branch is and what the branch is called, don't worry, we will get there. And why do we not number the other way? One, 2, 3, 4, 5, 6, which would also give us a hexane, is because you want your branches to be hanging off the lowest number carbon possible. And that's going to be one of our next rules on the next slide. So you can see with this numbering right here that we have our branch hanging off of carbon 4. Whereas with the other numbering system, if we had our longest continuous chain like that, we would have our branch hanging off carbon 3. And again, that's one of the rules that we will get to on the next page. All right, so this chain would be called what? The one on the right-hand side. It's principal. That would be a hexane. Now, it is not called just plain old hexane. It is something else because of the branch hanging off of there. Same with this one right here. It's going to be something hexane, and we're getting to that in this next slide right here, okay? Or it might be in the next one, because number 3 says if 2 chains are equal in length, so say you have 2 hexanes that are possible, You want to select the one with the most substituents or the most branches. Same thing, substituents and branches. So let's take a look at the molecule on the left. Now we can have 1, 2, 3, 4, 5, 6, like that. And we would have one branch here and a second branch right there hanging off of carbon 3. So we'd have a 6-membered longest continuous chain, so that would be called our parent. And then we would have 2 branches hanging off of that. If we were to number it differently, so say we said, no, I want to go ahead and number it this way, which is also a hexane, so you have the same length for your parent chain. What we would have is we would only have 1 branch. So even though that looks strange, like it could be 2 branches right there, you can see that this right here, there's only 1 arm that connects that carbon and carbon right there. So you have 1 branch hanging off that 6-carbon chain. So you would not want to do that because you want to select the one with more substituents. And that's what the molecule on the right shows us. It says that you're going to go ahead and identify the 6-carbon chain that runs left to right horizontally right there and has 2 branches hanging off of it, rather than this one right here that has 1 branch hanging off of it right here. Why? Because those are the rules and we want to be consistent. Okay, number 4 says number the principal chain, giving the lower number to the first branching point. So we talked about that on the previous slide, how if you have a choice in numbering, you're going to choose the numbering that would give you your branch on the lower number carbon. So see how below here we numbered left to right, and what we'll have is our CH3 branch right there hanging off of carbon number 4. Whereas if we number backwards right here, so 1 through 6 this way, we'll have our branch right here hanging off of carbon number 3. And IUPAC says that you want that CH3 to be connected to the lowest number carbon possible in the chain. So you would number the chain backwards. And this is going to give us 3-methyl hexane because we've got a methyl group, which is CH3, and we'll get to what the branches are called in just a little bit. Don't worry, just roll with it right now. A methyl group hanging off of carbon 3, and our 6-carbon chain is called what? Hexane. Yes. Okay. If we were to number it the blue way, this one right here, we would have 4-methyl what? We'd have 4-methyl hexane because the parent chain is 6 carbons long. Either way, if we number forwards or if we number backwards, we've got 6 carbons, and that's a hexane. The branch is CH3, no matter which direction you go, which is a methyl branch. And again, we'll get to what the branches are called soon, so don't worry about that. But if we number left to right, the methyl will be on carbon number 4. So IUPAC says this right here is the correct name because you want the lowest number possible for your branch or branches. Alrighty, friends, moving on. All right, number 5 says identify the name of each branch and to which carbon on the parent chain it is attached. So that's what we did in the previous problem. We said either we have a 3-methyl or we would have a 4-methyl, and we decided that the 3-methyl was the correct way to label it due to our rules. So that's identifying which branch it is, because we said a CH3 is a methyl, because I told you it was a methyl, and the location is right here. Okay, so now on to what the heck is a methyl, and how did I know what that was, and how are you supposed to know what that is? Well, methyl comes from methane. And methane is something that we learned in previous lectures. It is a single carbon with 4 hydrogens. So CH4 is called methane. And if we draw it out, the full structure, it looks like that. Now, if we take one of the hydrogens off, so we rip that off, so it takes off, says bye, and we're left with this right here, which is also symbolized like this, which you can see right here. That goes from methane, you can see right here, and we take the ANE off, and we add YL, not YL, the YL sounds like ill. So we take off the ane and we add ill, and this becomes methyl. So that's a methyl group, okay? Now it's gonna attach to a parent chain, and often we'll just go ahead and put an R to indicate some kind of parent chain that methyl is connected to. And you can remember that because it means just the rest of the molecule, R for rest of molecule, okay? So that's a methyl group. And then if you have a 2-carbon chain, that looks like this if we draw it out. And that's going to come from ripping a hydrogen off the end of an ethane. So our 2-carbon hydrocarbon is called ethane. And when we do that, what we create is an ethyl. So we take the ane off the end of ethane and we add a YL, and then we get an ethyl. Now we can stick that on the end, not the end, in the middle of a longer hydrocarbon, and that'll be a branch. So sometimes, again, you'll see an R here just to indicate the rest of the molecule. Now, an ethyl group can also be written like this. That's just the shorthand that's just going to tell you how many carbons and how many hydrogens you have. Whereas this one over here is going to give you a clue to the structure. And then that's the full structural formula. Okay, so if we have something that has 3 carbons there, it's not going to be a propane, it's going to be a propyl, okay? And the YL is indicating to you that it is hooked onto a larger parent chain. So it is the smaller carbon chain, so it is the branch or the substituent. Now, putting that into a chart form, we have this right here. So you can see all of the hydrocarbon, branches that I'd like you to know here. And I'm going to put a check mark next to the ones to definitely know. And you must know methyl, ethyl, propyl, butyl, isopropyl, and tertibutyl down there. So methyl, ethyl, and propyl, we've gone over. They come from methane, ethane, and propane. And butyl comes from what? It comes from butane, and butane is a hydrocarbon that has 4 carbons. So you can see right here, we've got 4 carbons. Now, isopropyl, what on earth is that? Well, if we look at the structure here, we can see that it has 3 carbons. So it's a 3-carbon chain. But what's the difference between that and the 3-carbon chain right there in propyl? Well, in propyl, what happens is that the parent chain is going to attach to one of the end carbons. And in the isopropyl, the parent chain is going to attach to the middle carbon, this one right here. So what that will often look like is, say we have a large hydrocarbon chain there, and we put a little snake tongue like that on the top, and this group right here would be your isopropyl. So what you would have is you would have a carbon here, here, and here, and each of these carbons on the ends would have 3 hydrogens, and that carbon in the center right here will have how many hydrogens on it? Well, you can see right here it's only got 1, and that's because, remember, carbon's like an octet, and that carbon in the center there is already connected to 3 other carbons. There's a carbon in the parent chain right here. So it only has room for 1 hydrogen. It's not like the middle carbon of the regular old propyl there that is CH2. So you got to watch it on that one. You can also point it down. So say we've got this molecule right here. You can put your isopropyl like that. You can also draw it with the C's and the H's. We can show it on a piece of paper in a number of different ways. Now, isobutyl and sec-butyl, those ones we don't run across as often as the other ones, so those ones don't worry about getting to know a whole lot. Now, the terse butyl down there, we more often call it T-butyl. And that's exactly the same thing. Terse butyl and T-butyl, we can use that interchangeably. Now notice right here that this structure kind of looks like a T. And that's what it's gonna look like on a molecule when the T-butyl is a branch. And it looks like a T, so T-butyl, that's kind of easy to remember. So we would just draw something like that. Now, if you wanted to put all of your carbons and your hydrogens in, that would take a little bit of time, but it looks like this. And let me squish these guys over here. And this carbon in the center right here, my friends, how many hydrogens is it connected to? Well, if we look at the structure over here, you can see that that carbon in the center right there doesn't have any hydrogens on it. And that's because it is single bonded to 4 other carbons. So there's a carbon in the parent chain right here, and at every point and every end, and you can fill in all those hydrogens around all of those carbons if you want to, but I don't want to. But they're there. That's the glory of the line bond formula, is you don't have to draw in your hydrogens. Okay, so that's why we don't have a hydrogen on that center carbon right there, because it already has its octet. It doesn't need any hydrogens. Alrighty, folks, moving on. So let's put all this together again. We already did it on another slide, but let's take a look at this molecule right here. So what we did is we decided that we were going to number right to left, so we're going to number backwards. So we identified that that horizontal carbon chain was the longest carbon chain possible, continuous carbon chain possible, and that we have one branch right here, one thing that would have replaced a hydrogen on that carbon number 3, and it is called methyl. So, where is our branch located? Well, it's on carbon number 3. What is our branch? It's methyl. And what is our principal or our parent chain? Well, it has 6 carbons, and that's called a hexane. So right here you have the parent. Right here you have the name of your branch. And right there you have location of branch. Now notice when we have a number and a letter next to each other, we use a hyphen. And there is no space between the branch and the parent chain. So this is called 3-methylhexane. And the rules tell us how to name it. Number 6 says, how do you name it? Which we already did in number 5. So to construct the name, you put the location of the branch, the name of the branch, and what the parent chain is. So number 6 is just telling you in bullet pointed form the rules for naming the molecule we did right here. And the molecule on this slide is another 3-methylhexane. And again, it describes for you how to do that. Alrighty, let's get to some problems. So let's do the top left. Now the first thing we have to do is identify the longest continuous chain. Most of the time we're going to try left to right first and see if that works. So what we have here is we've got 1, 2, 3. Okay, so we've got a propane there. So let's see if anything else is longer. 1, 2, 3. Nope, we got another propane. What about if we did 1, 2, 3? Nope, another propane. What if we did 1, 2, 3? Nope, another propane. So it looks like our parent chain here is going to be what? Propane. Yep. Okay, so propane there. All right, this might end up being an episode of King of the Hill. And if you don't know what I'm talking about, I guess you have to go watch it. All right, so the next thing is, how do we number the parent chain? Well, we can do 1, 2, 3, and our branch right here would be hanging off of carbon number what? Carbon number 2. Or we could do 1, 2, 3, and our branch right there would be hanging off of which carbon? Carbon number 2. Okay, so that didn't really change things there. What about if we numbered 1, 2, 3? Well, this looks a little bit different to most students, but this is again the same exact thing because there's your parent chain right there, and you've got this CH3 unit hanging off of which carbon? Carbon number 2. And what does that look like if we draw the bonds in, just to show you that it's the same thing? Okay, so if we call that the principal chain and we've got a branch hanging off of carbon number 2, this right here is the exact same thing as this right here. So no trickery going on here. It's just that there are a million different ways that we can draw the exact same molecule. Okay, so most of us, what we're going to want to do is we're just going to want to keep it simple and say, okay, we've got a principal chain that is 3 carbons long, and we have a methyl group hanging off of carbon number 2. So our branch name is methyl, and the location is carbon 2. Okay, so how do we put all those things together? Well, the location comes first, so the numbers are going to come first. So we're going to have number, and then we're going to have branch. And the branch starts with a letter. And when we have a number and a letter next to each other, what do we put between them? We put a hyphen. Because why? Because that's the rules that IUPAC made for us. So we have a 2-methyl, and then no space, and what comes next? Propane. You are right. We have 2-methylpropane. So we have a principal chain that's 3 carbons long, that's a propane, and we have a methyl group hanging off the second carbon of the propane. Okay, friends, let's move on to the next molecule here. So what we've got is 1, 2, 3, 4, 5. We've got a 5-carbon chain if we go left to right. If we go down, we would have a 5-carbon chain. If we go right to left, we'd have a 5-carbon chain. And if we go right to left and then down, we have a 5-carbon chain. So on this one, we're probably gonna want to keep it simple like we did with the one on the left, and number it left to right. And then we can see that we've got a branch hanging off of which carbon? Hanging off of carbon number 3. And always draw the circle around the branch if you're having trouble deciding what the branch is. That way you can see how many carbons are in that branch. Never, never, never include the carbon that is part of the principal chain. This carbon right here, this belongs to this chain right here. So you're going to want to draw your circle around the branch going through the bond right there. And now I'm getting a little bit too much in this picture, so I'll do a little bit of erasing there. Okay, so this is the branch right here. Now, do we see a problem here? Did we do something wrong? Are we good? I am seeing that we have a pentane. Is anyone seeing anything else? That's all I see is a 5-carbon chain is a pentane. All right, so our principal chain is pentane, because that's what a 5-carbon hydrocarbon chain is called. And we've got a branch. Now, the branch is hanging off of which carbon of the pentane? So we have a branch on carbon number 3. And the branch name is what? You've got a 2-carbon branch here. Well, if a 1-carbon branch is a methyl, then a 2-carbon branch is an ethyl. And remember, that comes from ethane. So what we're going to have is what? Name it for me. What comes first? 3, and then hyphen, because we're going to have a letter, and that's ethyl. And then what? And then pentane. So we've got a 5-carbon principal chain, which is called pentane, and we have a branch hanging off of it. Well, where is that located? Well, it's on carbon 3, and what is it? It's an ethyl. Okay, moving on to bottom left. Alrighty, friends. So remember with our line bonds that every point and every end is a carbon. So if you need to draw the carbons in for you so you can see where they're at, go ahead. Don't worry about drawing in all of the hydrogens because we're just naming it right now. We're not drawing it, so we need to know what the parent chain is. So if we do 1, 2, 3, 4, 5, 6, we'll have a 6-carbon chain. And if we do 1, 2, 3, 4, 5, 6, we'll have a 6-carbon chain. Okay, so that's possible. And if we do, oops, I got rid of my pen colors. Oh, there's some more. All right, let's do green. What happens if we do 1, 2, 3, 4, 5, 6? Well, that's a possibility. We could do that one too. So what do we do here? Well, what we're going to do is we're going to go with whichever direction gives us a branch at the lowest numbered carbon, because all of our principal chains here that we've identified are 6 carbons long. Okay, so how about we number it backwards? That way we'll get a branch hanging off which carbon? Off of carbon number 3. If we numbered it left to right, what we would have is we would have a branch hanging off of carbon number 4, and we don't want that. So let's get rid of those ones. All right, so where is the branch? What is it? Well, it's on carbon number 3, and let's identify it by drawing our carbons of the principal chain back onto the principal chain. So remember, longest continuous carbon chain. Let's also put them in the branch. Now, remember that you don't include the carbon that the branch is connected to in the number of carbons for your branch. So you're going to put the line splitting the bond right there. So this would be CH3 on the end, and you'd have a CH2 there. And when you have CH2, CH3, what is that branch? Well, up here, we said that that was ethyl, and it is. So what we have is we have 3-ethyl. So we've identified the branch. We've identified where it is. Now let's identify the parent chain. And a 6-carbon parent chain is called what? Hexane. So we have 3-ethyl hexane. Yay! Okay, now how do I get my pen back? There we go. All right, pen on the side there. So let's take a look at the carbon chain on the bottom right there. So we can do 1, 2, 3, 4, 5. Or we could do 1, 2, 3, 4, 5, 6. Okay, so maybe that one doesn't work. Or we could do 1, 2, 3, 4, 5, 6. So it would be this one. And if we do the one that I just highlighted, the branch right here would be hanging off of which carbon? It would be hanging off of carbon number 3. Okay, So let's go ahead and go back and compare that with another numbering, 1, 2, 3, 4, 5, 6. And we would have this branch right here. So both of our parents are going to be 6 carbon chains. So that's going to be hexane. And in the first numbering system, we had a branch hanging off of carbon 3. And in the one that I've just drawn right here, we have our branch hanging off of carbon number 3. So it looks like it doesn't matter which way we go. So let's stay with this one right here. So we have branch location is 3. And now we have to decide what that branch is. All right, friends. So let's get rid of that circle right there. And let's draw some carbons in here. So there are the carbons of the parent chain. And again, remember, you do not include the carbon of the parent chain in with the branch. So the branch is right here. So you have a carbon here and a carbon here. And if you don't know that a 2-carbon branch is called an ethyl, it might help you if you want to draw in all the hydrogens. So you can see that what you have is CH2CH3 in this branch, which we've done a number of times now. Here it is, and here it is, and that is called what? That is called ethyl. So the branch is ethyl. And if we put this all together, I'm going to write all of this up here so I have some space. That's going to be 3 because we start with a location. And then what? Hyphen, oops, not methyl. Bad teacher, bad. We're going to do, I'm going to switch to blue, sorry. 3 ethyl, and then what? Hexane. Now, what you might notice is that it's exactly the same thing as this one over here. Now, how is that possible? Come on, eraser. There we go. Let's erase the whole thing. Erase the whole thing. Oh, okay. Well, that's not going to work for me. So, there we go. Okay, there we go. Okay, back. All right, how is that possible? Those things look like way different. Well, the thing about this is these bonds, all of the bonds between all of the carbons and between the carbons and the hydrogens too, they all have free rotation, which means that this bond can rotate around like this, and that would bring this part of it over here. So it would look like that, and then that part wouldn't be there anymore. This is kind of hard to visualize. I need some models for you guys. And we can rotate these around. Anyways, you can rotate all these little pieces around until these two look exactly the same. I'm going to make you another video you guys can click on where I make the models and show them to you. All right, moving on. Let's draw something. Yay! Let's draw 4-isopropyl octane. Alrighty, now octane, how many carbons does that have? That has 8. That's one of those easier ones that we usually know. So we have 1, 2, 3, 4, 5, 6, 7, 8. Whew, okay. So if we were to draw all of the bonds, so all of our carbons have 4 single bonds, so they all have their octets, and all of our hydrogens have their duets, what we would have is this. Now, I didn't draw a hydrogen on that fourth carbon because we've got a branch there. And how did I know that? Well, I can see 4 isopropyl there. Now, propyl, remember, has how many carbons? Propyl has 3 carbons, but an isopropyl also has 3 carbons, but a slight difference. The isopropyl has the carbon in the middle connected to the parent chain. So there's going to be a carbon on either side. And I'm going to draw the left carbon up there just for space. All right, so I've got an isopropyl up there, and what we can do is we can add in the hydrogens because we're already drawing full structural format here. So give it a lot of extra space. And what are we missing there? Well, look at this carbon right here. What's the problem there? Well, it's upset because it only has a sextet. So it has 2, 4, 6 valence electrons around it drawn. So we need it to have an octet. So there's probably what connected to that carbon there? Probably a hydrogen. And we just need to squish it in somewhere. So we can add it to the left side, or you could have put it up or to the right. It doesn't matter as long as it's there. Now, this bond right here, I just drew it all huge and long so I could have some room to connect the isopropyl. And you can see that drawing out the full structural formula is pretty tedious. So again, with all molecules, we can draw them in a number of different ways. So we could also do the condensed format. So we'd have CH3, which is this on the end here, and then a couple of CH2s, and then a CH, which is this right here. Now notice it's not a CH2, it's a CH. And we could connect that with CH, CH3, and CH3, which is the isopropyl up here. And then we have the rest of the molecule over here, which is CH2, 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 and CH3. And oops, I forgot the hydrogen on the end there. Bad, teacher, bad. Okay. Could I make this even easier on myself? Why, yes, I could do like a super condensed format where I take these 3 CH2 units and throw parentheses around them and say I've got 3 of them. And then you could do that on the other side over here also. That won't save you much time, but it'll save you time. But if you wanted to save a lot of time, you would do the line bond structure, which is my absolute favorite because I love drawing things that look like caterpillars. So what we would do is once we put our pen down on the paper, we count 1. We haven't drawn any line or anything yet. So we go 1. That's right there. You don't have to draw a circle. I'm just saying I'm putting my pen down. 1, 2, 3. Now, why did it do that? Oh my goodness, technology. Okay, let's switch to blue then. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8. I could have started with my left hand carbon up. And what I mean is I could have said 1, 2, 3. Oh, stop it. 1, 2, 3. Okay, stop doing that. 1, 2, 3, 4, 5, 6, 7, 8. Either way, you've got 8 carbons there. And on the 4th carbon, I need an isopropyl. So we've got 1, 2, 3, 4 there. And in line bond structure, an isopropyl looks like a little forked tongue, like that. And you can draw it up. Or if we had this molecule down here, 1, 2, 3, 4, what you would do is you would draw it down like that. Okay, now yes, you could have numbered your hydrocarbon chain backwards. So if we erase our numbers here, and we would have gone 1, 2, 3, 4, 5, 6, 7, 8 like that, we would have put our isopropyl somewhere else because we've got a 4 isopropyl, not a 5 isopropyl. So we'd have to go ahead and get rid of that right there. Don't erase, no, it erased my whole thing. 1, 2, 3, 4, 5, 6, 7, 8. There we go. That's connected. Okay, so then we would have our isopropyl hanging down off of carbon 4 like that. So if your point points up, then you would draw your branch pointing up. And if your point points down, then you draw your branch pointing down. That's just convention. You don't want to draw a branch in between those two mountains like that. That's just not how we do it. Why? Because chemistry. Okay, so we're going to end this video right here, and we'll keep going on with number 7 in the next video. Okay, friends, bye-bye.